Hello everyone. So for today, we're going to talk about another lesson and welcome to a session filled with new learning. So before we begin, I will ask you to breathe in, breathe out, breathe in, breathe out. Okay? So what material is involved when you perform that simple activity? Okay, very good. So gases. Okay, so what comes out from your mouth are gases. And we know that gases have properties very different from solids and liquids. They behave differently from solids and liquids. So for this session, we are going to learn about pressure and their unit. We are going to talk about gas laws to determine pressure, volume, or temperature of gas under certain conditions of change. We are going to use the ideal gas equation to calculate pressure, volume, temperature, or number of moles of a gas. Use Dalton's law of partial pressure to relate mole fraction and partial pressure of gases in mixture, and apply the principles of stoichiometry to determine the amounts of gaseous reactants and products. And finally, relate the rate of gas diffusion with molar mass. Okay, so since our first target is to know what pressure is, because this is very important in the understanding of the behavior of gases. Okay, so what do you know of pressure? Okay, so pressure is the result of force that is produced when gas particles hit the walls of a container. This is also a force acting on a specific area. And to get the pressure, we apply the formula force over area. So in gas laws, pressure have lots of units. And these are the unit used for representing pressure. First, we have atmosphere. ATM stands for 1 atmosphere. 1 atmosphere is equivalent to 760 millimeters of mercury, also equivalent to 760 Torricelli in honor of Evangelista Torricelli, who invented barometer. So in the international system of units, we make use of Pascal. It's equivalent to 101,325 Pascal. And we also make use of inch mercury, and that is 29.9. And for pound square inch is 14.7. And another unit for pressure is 1.013 bar. So these are the common units that you will encounter in solving problems involving gases. Okay? So it's a must that because we have lots of units of pressure, it's a must that you know how to convert one unit to the other. Okay, so say for example, a pressure of 7,500 atmosphere, what is it in millimeter mercury? So converting pressure or unit of pressure is easy by simply applying dimensional analysis or factor label technique. So here you are going to make use of the um, equivalent of 1 atmosphere, which is 760 millimeter mercury. And to convert, so we have for every 1 atmosphere of 760 millimeter mercury, so we have to cancel atmosphere. So we have 7,500 times 760 is 570 millimeter mercury. Okay? So getting the equivalent, the desired unit in pressure, we simply do cancellation technique. And here we are going to make use of the factor, the equivalent of atmosphere to millimeter mercury. Okay? So also, we have for Torricelli, given 50 Torricelli, what is this in atmosphere? So since 1 atmosphere is 760 Torricelli, we can simply convert 50 torricelli to atmosphere. How? So we have now 50 torricelli divides 760. Okay? And that is 700 atmosphere. Okay? So that's how to convert one unit of pressure to the other unit. Okay? So after learning how to convert unit in pressure, so we have to, in understanding the behavior of gas law, which is stipulated in the KMT or the kinetic molecular theory, we have to familiarize ourselves with the important quantities for gases. And these are first, amount of gas, which is represented by mole, or the SI unit for that is mole. Temperature, it's always in Kelvin unit, and pressure in Pascal in the SI, and volume is liter. Okay? So amount of gas, it's all about mole. And then for degrees Celsius, to convert that to Kelvin, we simply add 273. Okay, for pressure, there are lots of unit used, but in the SI, it's Pascal, and volume is the space occupied by gas, and it's usually expressed in liter. Okay? Or sometimes it's in milliliter. Okay, so the first gas law that we need to deal with is all about Boyles Law. Okay, so what you know of Boyles Law? Okay, so it was Robert Boyle who identified the relationship of pressure and volume of gas when the temperature and amount of gas is kept constant. And how did he describe the relationship of pressure and volume? Okay, so it's inversely proportional. Okay? So inverse proportionality. So when one is high, the other one is low, and vice versa. And the mathematical equation for Boyle's law is P1 V1 is equals to P2 V2. So for two conditions, initial and final. P1 is pressure 1, volume is initial volume, V1, and then P2 is final pressure, and V2 is final volume. Okay? So this is how graphically pressure and volume relationship is described. So here in the y-axis and the pressure, and then the x-axis is the volume. So you notice here that as pressure goes high, then the volume is low. But when the pressure is low, the volume is high. So that's the inverse relationship of pressure and volume. Okay? And when we apply that the problem, say for example, for helium gas occupying a volume of 250,000 liter and 800 torricelli, it's a pressure. So if the volume is changed to 500, what is the new pressure? So here in Boyle's law, you will just consider the pressure and volume. So initially, it's 250,000 liter, and the initial pressure is 800. So what will happen to the pressure if the volume is changed to 500 milliliter? So before you solve, you look at the unit of liter and milliliter. So you have to convert milliliter to liter. Okay, and that is 0.5 liter because 1,000 milliliter is 1 liter. Okay, so you need to find the new pressure or the P2 from the original equation of P1 V1 is equals to P2 V2. How will you derive the formula for final pressure? Okay, so final pressure is P1 V1 over V2. Then substitute the values. Okay, so we have initial pressure of 800. You multiply that to final initial volume, and then you divide it to the final volume. So what happened to the pressure? So if you notice, since the volume increases, so expect that the pressure will decrease. Okay? So from 800, it's now 400 because the volume increases, therefore the pressure decreases. So that is the inverse relationship of pressure and volume. So that is Boyle's law. And when can we observe this inverse relationship? So with the use of syringe, I understand that you are very familiar with syringe. Okay? So when you make use of this one, you will observe that pressure is really inversely proportional with volume. Okay? So another gas law that we need to talk about is Charles' law. Okay? So it's Jean-Jacques Charles who formulated Charles' law, and here he described the relationship of volume and temperature. So how is volume related to temperature? Okay, so they are directly proportional. So when we say directly proportional, as one increases, the other one is also increases. So to represent it mathematically, we use initial volume over initial temperature, so for two condition, and then it's equivalent to final volume over the final temperature. Or we simply represent it using initial volume, final temperature is equals to final volume and initial temperature. Okay? So this is how a direct relationship is described. So here you will notice the relationship of volume and temperature. So in the y-axis is volume, in the x-axis is temperature. And you see that as the temperature goes high, the volume is also getting higher. Okay? So if we have syringe as the practical application of Boyles Law, this time let's have for Charles' Law. So for Charles' Law, we can observe this in how bread expand when baked. So for those who experience baking, you will notice that the bread expands when put or placed into the oven or microwave oven. So as the temperature increases, the gas inside, the yeast, the gas inside, the gas that were released is heated and then it expands. So making the volume of the bread bigger. So it's fluffy. Okay? So that's the application of Charles' law. So if we have this example, say a sample of neon gas at 716 millimeter mercury has an initial volume of 10 and the temperature initial is 34 degrees Celsius. So what is the new volume if the temperature has been increased to 75 degrees Celsius, maintaining the same pressure? So take note, pressure here is constant. So initially the volume is 10. So what will happen to the volume if the temperature increases from 34 to 75? And take note, in temperature, it's always expressed in Kelvin. And to do that, you have to add it to 273. Okay, so we have 307 and 348. So we're asked to find the final volume. So here, given the relationship, okay, we can solve the unknown by applying the formula initial volume, final temperature over the initial temperature. Okay, and substitute. Let's see what had happened. So we expect that in this problem, the volume will increase. So from 10, what happened? Okay, so it's now 11.33. Why is that so? Because the temperature increases from 307 to 348. Therefore, the volume will also increase from 10 to 11.33. Okay? So next is the Gay-Lussac's law. Okay? So what variables are being described in Gay-Lussac's law? So Joseph Louis Gay-Lussac explained the relationship of temperature and pressure. Okay? And what do you think is the relationship between temperature and pressure? Okay, very good. So they are directly proportional. So as the temperature increases, pressure also increases. Okay? So mathematically, we can represent Gay-Lussac's law as pressure 1 over initial temperature is equals to final pressure over the final temperature. So here, the volume of the gas is kept constant. Okay, so we can simplify this by using P1 T2 is equals to P2 T1. Okay, so this is how graphically we can describe pressure and temperature. So as the temperature increases, the pressure also increases. Okay, so we can observe Gay-Lussac's law using when we are making use of pressure cooker in cooking. So we understand that in pressure cooker, the main reason why food is cooked at a shorter period of time because the steam or the gas is trapped and the pressure is was built up when you increase the temperature. Okay, so pressure cooker is an application of Gay-Lussac's law. So consider this example. So you know what aerosols are. Okay, they are dangerous when they are heated because they can explode. So suppose a can of insecticide with a pressure of 4 atmosphere at a temperature of 28 degrees Celsius is thrown into a fire. If the temperature of the gas inside the can reaches 400, what will be its pressure? Okay, would you expect the can to explode if the maximum safe pressure is 8 atmosphere? So here in Gay-Lussac's, we have pressure and temperature. So pressure here is 4, okay, 4 atmosphere, and initial temperature is 28, and then final. So the temperature increases. What can you expect with the pressure? Okay, so it will also increase. So let's see, and let's see if the can will explode if its safe pressure is 8 atmosphere. So given that problem, we have to find the final pressure in atmosphere. Okay, so from the original formula, we can derive final pressure into P1 or initial pressure plus P2 times P2 over T1. So substitute the values. So now the final pressure is 8.94. So from 4 atmosphere, it's now 8.94 atmosphere. So it increases. Okay, because the temperature also increases. So will the can explode if the safe pressure is 8? Okay, very good. Definitely yes, because it exceeded the maximum safe pressure, which is 8 atmosphere. So we are not allowed to throw empty aerosol cans in fire because of the possibilities of explosion. Okay, so this is all about Gay-Lussac's law. Okay, next we have the combined gas law. So combined gas law is actually the combination of the three, Boyles, Charles, and Gay-Lussac's. So here we incorporated three variables: pressure, volume, and temperature. And for two conditions, for the initial and final, so we can make use of the formula P1 V1 T2 is equals to P2 V2 T1. Okay? So for the combined gas law, say for example, we have 30 milliliter sample of bubble is released from a diverse air tank at a pressure of 4.5 atmosphere and a temperature of 15. So what is the volume of the bubble when it reaches the ocean surface where the pressure is 1 and the temperature is 20? Okay, so we know that in the ocean, the temperature and the pressure on the surface water and below is different. So let's see the changes in the volume of the bubble if it is brought on the surface water. So we have here in combined gas, so you have to check pressure, volume, and temperature. So by analyzing the given, so we have here an initial pressure of 4.5 atmosphere, volume of 30, and a temperature of 298 Kelvin. So at the surface, the final pressure is 1 atmosphere and 293 Kelvin is the temperature. Okay? So what is the final volume of the gas? Okay? So let's check. So by applying our formula, you derive the formula of the unknown, which is the final volume. And to substitute, let's see what had happened to the volume of the bubble. So from 30 milliliter, it will increase to 132.73 milliliter. Okay? So you see the effect of a change in temperature and pressure to the volume of the gas as the condition changes. So when you are below the ocean or under the ocean, and when you are on the surface. Okay? So this is all about the combined gas law. So this time we'll be moving on to Avogadros Law. So Amedeo Avogadro talks about how, take note, Amedeo Avogadro is very known for the introduction of mole. So in Avogadro's law, we consider the relationship of volume and the amount of gas. Volume of the gas and the particles of gas in mole. So he described that at standard temperature and pressure, so we call it as STP. That STP is 273 Kelvin and 1 atmosphere. So he mentioned that 1 mole of any ideal gas will occupy 22.4 liters of gas. Take note of that. 1 mole of any gas will occupy, this is standard, 22.4 liters of gas. And that is at STP. Okay? And to describe the relationship of volume and amount of gas, obviously we can say that as the number of gas particle increase, the volume also increase. So it's directly proportional. So we can simplify the formula V1N2, V2N1. So here from the given, let's have certain temperature and pressure, 8 grams of nitrogen has a volume of 5 liters. What is the volume after 4 grams of nitrogen is added to the balloon? Okay, take note of this. So 8 grams of nitrogen. So here, the given is mass in gram, not in mole. So for you to get the mole, we have the given mass over the molar mass. Take note, uh, 8 grams is the given mass and nitrogen is diatomic. So it's 14 times 2, it's 28. So 8 divided 28 is 2900 mole. And what is the volume after 4 grams? So you have to add 4 to 8 grams, the initial mass. So you have 12 grams divided 28 gram per mole, and that is 4300 mole. So there is an increase in the number of particles of gas. So what are you expecting for the volume of this gas? Okay, of course, it will increase. So from the formula, we'll derive from the initial formula what is the final volume. So final volume is V1N2 over N1. So substitute all the values and let's see. Okay, so from 5 liters, it's now 7.41 liters. Okay, so it increases. As the number of particles of gas increase, the volume also increases. So that's Avogadro's law of volumes and moles. Okay, next is all about the ideal gas law. So ideal gas law is actually the combination of all the gas laws. So here you will find pressure, volume, amount of gas, and temperature. So it's the combination of all the gas laws. And here we can find all the quantities or all the variables for gases. And there is no condition here, the initial and the final. And for ideal gas law, we'll have the equation pressure volume is equals to mole. R is the constant and T is temperature. So take note that R constant can be computed by applying PV over NT. And what is that R? So we have to consider all the conditions at STP. So at 1 atmosphere of pressure, a volume of gas is 22.4 liters. You divide that to N, 1 mole, and then the temperature of 273. And that R is equivalent to 0.08205 liter atmosphere mole Kelvin. So take note, this is constant. So the value of the R will always be this one. Okay? So again, for ideal gas law, it's PV nRT. So here, calculate the pressure exerted by 3,000 mole of gas contained in an 8-liter vessel at 18 degrees Celsius. So this time, you have to make sure that all the units conform with the standard Kelvin, mole, liter, and atmosphere. So here, 18 degrees Celsius will be converted to Kelvin. And, okay, so let's see. The question here is, calculate the pressure. So what is the pressure of the gas? If initially the volume is 8 liters, and the amount of gas in mole is 3,000 mole, and the temperature is 291 Kelvin. So substitute from the formula PV nRT, our unknown is pressure. So we have nRT over V. Okay, so here the pressure in that container is 90 hundredths atmosphere. Okay, so ideal gas law is the combination of all the gas laws. Okay, next is all about Dalton's law of partial pressure. So here in Dalton's law of partial pressure, it is described that the total pressure exerted by the mixture of gases is equal to the sum of the partial pressure of the gases present. So in a container with a mixture of gases, the total pressure in that container is merely the sum of the partial pressure exerted by the mixture of gases inside that container. And the pressure each gas exerts in a mixture is called the partial pressure of the mixture. And to get the total pressure, it's just simply the summation of partial pressure of the first gas, second gas, third gas, and so on. Okay? So say for example, what is the total pressure in atmosphere? Take note of that. Of a gas mixture containing argon, 28 hundredths atmosphere, helium gas at 280 millimeter mercury, and nitrogen gas at 300 torricelli. So take note, before getting the total pressure, see to it that all the units are in atmosphere. So you have to convert 280 millimeter mercury to atmosphere and 390 torricelli to atmosphere. And that is 37 hundredths atmosphere for helium, and for nitrogen, 51 hundredths atmosphere. So after making all the units the same, we can now get the total pressure in that container in atmosphere. So we simply add, because total pressure is the summation of all the pressure of the gas. So we have 1.16 atmosphere. So that container exerts a pressure of 1.16 atmosphere. So after adding all the partial pressure of the gases inside that container. Okay? So next will be gas stoichiometry. So by now we understand what stoichiometry is. So this is all about computation of the amount of reactants or products in a chemical or in a balanced chemical reaction. So this time we are going to make use of the idea of gas. Okay, in finding out the mass relationship. So this is all about calculations involved mass relationship in chemical reaction where a gas either a reactant or a product. Okay? So here in gas stoichiometry, we simply rely on the idea or make use of the idea of ideal gas law, wherein we make use of PVMRT. That is if the molar mass of the gas is known. So we simply get the mass by applying the formula pressure, volume, molar mass over the R constant multiplied to the temperature. So for density, we can also get the density of gas by making use of M over B, where M is pressure times molar mass and volume is equals to R constant multiplied by temperature. Okay? So given this example, let's have for potassium chlorate. Okay, 2 moles of potassium chlorate will yield 2 moles of potassium chloride and 3 moles of oxygen gas. Okay, so given 50 grams of potassium chlorate, how many uh, liters of oxygen gas can possibly be produced? So from the given 50 grams of potassium chlorate, so we have 2 moles multiplied by the molar mass of potassium chlorate, and that is 122.55 grams per mole. In the part of oxygen, so take note a while ago, according to Amedeo Avogadro, for every 1 mole of the substance, it will always occupy a volume of 22.4 liters. So therefore, since oxygen is 3 moles, you multiply it to 22.4 liters. And how many liters of oxygen can be produced? Okay, so we have 13.71 liters. So for every 50 grams of potassium chlorate that will be decomposed, and we can possibly obtain 13.71 liters of oxygen gas. So this is all about what is gas stoichiometry. Okay? So the last part, it's all about effusion and diffusion. So effusion and diffusion can be used interchangeably, but in chemistry, they mean different, but they are related. Okay, so it was Thomas Graham who formulated the law of effusion, so which states that the rate of effusion or diffusion of a gas is inversely proportional to the square root of its molar mass. So we expect that if the molar mass is high, its rate is low. If the molar mass is low and its rate of effusion or diffusion is high. Okay? Just this inverse relation, but it's inversely proportional to the square root of the molar mass. Effusion is actually the movement of gas particles through a tiny hole. So in a container, when gases are placed inside and when there's a small hole, the gas will move out from that container. That's effusion. But on the other hand, diffusion is the process by which a gas is spread or mixes with another gas. Like when a cologne is used, when you spray that in a room, it will scatter or spread because it will mix with other gases and it will be brought in different parts of the room. So that is actually diffusion. Okay. So for the equation for effusion and diffusion, so here you'll see that rate A. So when we talk of rate, so we are talking of speed or time here. So rate A over rate B, so we are comparing two gases here, is equivalent to the square root of the molar mass of the B and the molar mass of the A. Okay? So say for example, it takes 110 seconds for a sample of carbon dioxide to effuse through a porous plug and 275 seconds for the same volume of unknown gas to effuse under the same condition. So what is the molar mass of the unknown gas in gram per mole? So here there are two gases involved. One is carbon dioxide and one is unknown. The carbon dioxide effuses at 110 seconds, and the other one, the unknown, is 275 seconds. So how can we find the molar mass of the unknown gas? Using the rate, the formula, rate 1 over rate 2 is equals to the square root of the molar mass of the gas over the molar mass of the second gas. So here, substituting all the values, so we have 275 seconds, that's the unknown, is to 110 seconds is equals to the square root of the unknown. That's the molar mass of the unknown gas. And then the molar mass of carbon dioxide is 44.01 gram per mole. So finding the molar mass, will have 44.01, and then you multiply it to 275 square and 110 square. So 44.01 gram per mole, multiply it to 275 square divided to 110 seconds squared. okay, is equivalent to 275.06 grams per mole. So that's the molar mass of the unknown gas. Okay? So this is what effusion and diffusion is all about as far as gases are described. Okay? So that's the end of this session. So I hope that you learned something from this discussion. So see you next time. Bye-bye.